All right, good morning. Let's do more Lewis structures. So, um, we're going to talk. We're going to start with just a couple more examples today of doing some Lewis structures using both methods, um, and then we'll start talking about delta H, which has never left us. We'll have a little bit of that going on, and we can also then talk a little bit about what's actually happening in the bonds and some polarity information there. So we're going to talk about both of those today because this chapter is sometimes it's two chapters, sometimes it's one. The one in our book currently it's two chapters, so we have 2 weeks for it, which is nice. So it'll probably be a little bit shorter of the video today, which is nice, I guess, because you have your exam on Monday, so you can be spending more time preparing for that. But chances are probably you're not watching this anyway until after, so either case doesn't matter. So let's look at a couple more. Um, all right, let's look at this dude. Let's see if we can do the Lewis structure for this particular ion, IO3 plus. Here's method one. We'll work through this. Um, as with before, it's a good idea, pause the video, try and do it, then resume it and see if you're working on it correctly, and if not, try and figure out what's the problem that's happening. Okay, if you're not. So total valence electrons here, we have 7 plus 3 times 6 minus 1. Don't forget, for a positive charge, you subtract electrons. So that's going to be 24. We're going to start with our skeleton. Our skeleton takes up 6, so we have 18 left. We have those 18. We have none left for our iodine. So let's go ahead and figure out what to do next. Well, our iodine only has 6 electrons, right? So we're expecting it to want some more. And so we're going to go ahead and see, well, we have 6 electrons here. We've got 8 on all these other ones. So let's just go ahead and make a double bond. I'll just choose to do it there. And so now everything's got 8. And so we want to now check the formal charges. Um, this one, hopefully by now we recognize the formal charge is 0, double bond oxygen. Oxygen with 2 bonds has a formal charge of 0. Oxygen with 1 bond and 6 electrons has -1. These are ones we've done before. But the iodine we haven't. So let's take a look at the iodine. Iodine should have 7 valence electrons, 4 bonds, 0 lone pairs, lone pair electrons. So we have a +3 formal charge there. And so what we'll probably want to do, since we know we want to mitigate the formal charges, again, this is still an area of debate in chemistry, but we're going to want to probably, since I have made the determination that for consistency in the class, we're going to be predominantly using the ones that minimize formal charges. So to make the most stable structure. And so to do that, we're going to want to make 2 more double bonds, because that'll get rid of the negative charges. It'll every time we take a lone pair, turn it into a double bond, that's increasing our formal charge. So we're at -1, we want it to be 0, so we're going to go ahead and make another bond with both of those oxygens on the left and the bottom. And so we're going to get iodine double bonded to 3 oxygens. Formal charge there is now +1. because we've added 2 more bonds. So now we're at 7 minus 6 minus 0, which is plus 1. And that's something unavoidable because this is a polyatomic ion with a plus 1 charge. So as a result, this will be our structure. And ta-da, we're good. All right, let's look at method 2. Method 2 for us. We're going to put them all with their valence electrons. Iodine has 7, the oxygens have 6. Positive charge means we are going to remove one from the central atom. So I'm going to just put a little X there. That's the one we're getting rid of. Right? Doesn't matter which one you get rid of, but that's the one I'm getting rid of. So there it is. It's gone now. So that's our positive charge taken care of. So now we just need to connect the dots. So we want to pair off everything that's on the outer atoms that's unpaired. That's what we care about. We don't care about the central atom because that's the way we are. And lo and behold, we end up, therefore, with this. And since we know we did the positive charge, we took away from the central atom, that's where our positive charge lies. And so that's our Lewis structure there. All right, so very exciting. So again, faster method, IMO, but we're going to see just shortly what's going to happen with a few circumstances. So this is a hypervalent species. The iodine has 12 electrons on it, which is allowed because iodine is big enough to accommodate all of these oxygens, and it's got the space in d orbitals to allow some electron overflow. So it's got two things working for it there. All right. Any questions on the, I don't know, what is this ion called? Iodonium, maybe? It's not one that we typically learn, but it's great for doing Lewis structures. Let's do nitrate then. Let's do nitrate. So nitrate, we have 5. Our total electrons is 5 plus 3 times 6 plus 1. Remember, negative charge means we add 1. So again, we're going to have 24 electrons here. Let's go ahead and do our skeleton. And just like last time with the iodonium, assuming that's the name, I'm sorry, I don't remember the name of that thing, it'll take our last electrons, which leaves us with none. And so we're going to see nitrogen is not got a complete octet, so let's go ahead and make a double bond. So now nitrogen has an octet. Hooray. They all have 8 electrons now. Formal charge on these oxygens, -1, 0. On the nitrogen, 5 minus 4 minus 0, plus 1 formal charge there. However, we can't do anything more to this Lewis structure. There's nothing else we can do to make this better. There's no way to mitigate these formal charges. Normally, our way to do that is to take a -1 formal charge and a +1, make a double bond between them, and poof, now we have fixed the problem. But if we try to do that, I'm going to do it in red so that we know it's a no-no. If we try and do that, indeed, we have formal charges of 0 on all these things now, but nitrogen cannot accommodate an expanded octet. It cannot accommodate the expanded octet. So this is not acceptable. So as a result, we cannot do this adjustment of Lewis structure. So we're stuck with having two negative ones and a positive one. That's all we can do. We can't actually do this structure. Not allowed. Nitrogen is not big enough, and it's also not got a place to store extra electrons. There's no 2D orbital that's empty hanging around nearby, so it's not going to happen. So we're going to be left with the structure we have here. One double-bonded oxygen, two single-bonded oxygens. The single-bonded ones have a -1 formal charge, and the nitrogen will have a +1 formal charge. Overall, giving us -1, which is our polyatomic ion. All right, so the problem there, we can't minimize the formal charges because that would break our rules. And we're going to see that nitrate is also going to be a pain with the other method. So normally, we would draw them, and we're going to give one extra electron to an outer atom, and there it is. I'm going to redraw the other one because now it's kind of overlapped. So we've given our one oxygen an extra electron. So if we want to pair things off, got a problem here. So I'm going to pair those off, but if I try and pair, I've drawn this one poorly. I usually try to draw them because I know it's going to happen, but it's probably what will happen with you guys. If you try and do this, you'll get nitrogen with too many bonds. You'll get the negative charge on the oxygen there. This is the only part you have to be careful with this method. If you end up with a hypervalent species, something with more than 8 electrons, that is not allowed to have it, aka something in period 2, you're going to have to fix it by doing the opposite of what we normally do. So normally, remember, we would make the double bond to fix formal charges. Because now we have too many bonds, we're going to now make some formal charges instead. So we're going to take the electrons here and move them onto the oxygen. We're going to break that double bond to make it a single bond, and that's going to fix our structure. So we're going to end up the following. And I'm going to fix that oxygen on the left. Poof, done. So we, just like before, we're going to have a -1 and a +1 on the nitrogen. And so that will be our Lewis structure. And again, there's resonance here, of course, because we could have made our double bond on any of those oxygens. So just remember that as well. There are 3 different resonance forms for nitrate. So just keep that in mind as well. All right, so in either method, we are going to have the same structure for any compound we make. So we should end up with the same structure for both methods. All right, we just need to, if we're using the first method, remember a little bit longer, but just keep in mind, again, you can't exceed the octet on certain atoms. And with the second method, it's the same thing. And so you just have to consider how to fix it. And the way to fix that is to break a multiple bond and give those electrons as a lone pair instead to one of the outer atoms. Alrighty, so your homework for this is up, by the way. Um, there are 5 things due on November 7th. So the Lewis structure homework, we're going to have the molecular geometry homework, which is the next chapter. We have a hybridization worksheet, and then we have 2 labs. You guys have like 2 weeks to do them, so don't leave them all to the last minute. I would suggest, yes, I know you have an exam on Monday, but work on them. All right, even if you have to prioritize doing the written work before the labs. The labs, again, like you can do them late if you have to. However, it's still going to benefit you to do them sooner because it's more related to the material that we're covering. So I would do that. So nothing is due this weekend because I know you have your exam and y'all are just going to ask for an extension anyway. So I'm going to go ahead and give that extension. So, but you have to live with the consequences then of now everything due on one day. So even though that day it's 10, 12 days away now. So just keep that in mind. Don't let this pile up on you. All right. But again, if you're watching this the day before the homework's due, then good luck. Alrighty, so there we go. There's our nitrate structure. Let's talk now about some stuff we can do with these Lewis structures. We're going to see that next week we're going to talk about kind of shapes and polarity that are associated with these Lewis structures. So these Lewis structures are 2-dimensional, just ways of conceptualizing how molecules look. And we're going to see that in reality, there are geometries associated with these things. And as a result, the shape of the molecules can have pretty big impacts on the properties that the molecule will undergo. So we're going to see why methane, for example, is a gas for most temperatures up until really, really cold. Ammonia is also a gas at room temperature, but water is a liquid that boils at 100 degrees Celsius. We're going to see all of that is due to its shape and the characteristics of the bonding that are taking place there. So we'll see that next time. But we're going to, you know what? I wanted to do one more example. Let's do this one as a Lewis structure, and then we're going to talk about energetics of reactions using Lewis structures. All right, so let's go ahead and do this. So, xenon is a noble gas. Noble gases normally do not react, but we're going to see fluorine is so reactive that it will actually react with xenon. So it's an interesting thing, and xenon makes a couple of different compounds with fluorine. Let's use method 1. We have 8 plus 4 times 7, which is 36. Sound right? Yeah, I guess so. 28 plus 8, 36. Yep. Let's make our skeleton. So with this, that's 8 electrons. We have 28 left. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 4 more electrons, so we give them to the central atom. So now we have 0. Let's check, does everything have 8 electrons? That needs to have 8 electrons. Remember, we can go above 8 on our central atom, and because it's not in period 2, it's in period like 5. Everything's got 8. Do we have any formal charges? Let's check. Let's check the fluorine formal charge. We have 7 minus 1 bond minus 6 lone pair electrons. We have no formal charge on fluorine. On xenon, it has 8 valence electrons. It's got 4 bonds. It's got 4 lone pair electrons. So we have a 0 formal charge on xenon. And so we're done. That's it. And so we see here that xenon has 2 lone pairs on it, even though it has 4 bonds. So again, we have a hypervalent species here. So it can accommodate extras of these. One thing to note, by the way, PT dubs here. Fluorine and hydrogen will never ever make double bonds. So in no Lewis structure ever should you ever have fluorine or hydrogen double bonded to something. It does not happen for several reasons. Hydrogen is simply got 1 electron. It cannot physically make a second bond. But fluorine is what we're going to see the most electronegative element we have. It is an electron hog. It wants to keep them all for itself. And so it does not share electrons. And we're going to see, we'll mention it at the end here today, but that electronegativity will also determine kind of an unequal distribution of electrons within a bond, but we'll get there later. With method 2, we've got all my lone pairs. Method 2 just has us connecting. Remember, we always want to satisfy our outer atoms. We don't care about the central atom's electrons. We just have to pair off all unpaired things with our outer atoms. And then we just have to redraw everything. So notice we still have four electrons left on xenon. And so don't forget them when you redraw it. There's our bonds to fluorine. All those fluorines have 6 electrons, which they had previously. And now we have 2 more lone pairs to put on xenon for those 4 electrons. So don't forget they're still there. I'm going to draw them nice and big. 1, 2, 3, 4. And when we just draw them paired off. So even though they this in our work, they're unpaired. We've taken away their partner, as it were. Just pair them off again in your final structure. Or you can be very careful about which electrons you're pairing, but either way, you should end up with the same thing. So we end up with the xenon with 2 lone pairs and 4 fluorines on it. All right, so again, a hypervalent species. Cool. Alrighty, so that's that. Let's talk about delta H. We're going to see that bond enthalpy is another way for us to calculate delta H for a reaction. Because you thought we were done with thermochemistry, right? We're going to see that the delta H for a reaction can be calculated, nope, calculated, that's not really a U, very good, calculated from analyzing Lewis structures. And we might be able to say estimated as well. There's always going to be just a slight difference in calculating delta H for a reaction from a bond enthalpy versus, say, delta HF. Bond enthalpies are more kind of, I don't want to say theoretical, but they're kind of more theoretical. And so we will work with them. Let's look at an example. Let's actually write this out as molecular first. So we need 2 oxygens here. So with these, it's important that we draw all of these things out, or if we simply don't have the space to put a big old 2 there, so we know. With CO2, we know the structure for that. And I don't remember if we did water, but I'll just draw its Lewis structure. We don't really need the lone pairs for here, but we've got 2 of those as well. So when we're looking at these, with this sort of reaction, we could have gone to the back of the book and be like, okay, we're going to check out our delta HF for all of these compounds, and we're going to calculate it doing products minus reactants, right? And so we could do that. But we can also use the Lewis structures. So we have more tools now to do this. We're going to see that breaking a bond is always endothermic. We require energy to be put in to break a bond, whatever bond that may be. And as a result, we're going to see that forming a bond is always exothermic. And so, in fact, they are the same. If we were to take a CH bond and break it into carbon plus hydrogen, separate them, break the bond, this is an endothermic reaction, and it turns out that this one has a delta H of 413 kilojoules per mole. Conversely, if we were to put a carbon plus a hydrogen to make a CH bond, we would see that delta H would be negative 413 kilojoules per mole. Right? It's the exact same number, opposite sign. It takes energy to break a bond, but if you make a bond, you release energy. Remember, as always, everything wants as low energy as possible. That's the idea. So forming bonds is a good thing. It makes things more stable. It lowers their energy. That's the purpose of doing these things. We can calculate delta H for a reaction by taking a look at all of the bond enthalpies of bonds formed. I'm sorry, we're going to start with broken because we're going to always start with our positive bits. Minus the sum of the bond enthalpies of bonds formed. And we put that minus there to make sure that we have everything as exothermic. Because bond enthalpies are typically given to us as positive numbers. Just understand for when they're being formed, when bonds are being made, it's always exothermic. So we put a negative in this formula to indicate that. Remember that the sign switches to negative when you have an endothermic reaction. So let's take a look at a table of bond enthalpies, which I have here in Discord for us. Let's switch over for just a second. This is our Discord page, of course. I am in our extra resources tab here. If you scroll up just a little bit, and in fact, I can just copy paste this so we have it more recently. This is a table of bond enthalpies. And so looking at these things, we're going to be able to see how much energy is associated with either breaking or making one of these bonds. So for example, to make a hydrogen-fluorine bond, you would release 567 kilojoules per mole. If you were to break a sulfur-sulfur bond, you need to put in 266 kilojoules per mole of energy. All right, and then multiple bonds, we're going to see always have more bond enthalpy associated. Single bond, carbon-carbon, 348. Double bond, 614. Triple bond, 839. So the more bonds we have, the more energy it takes to break them, right? Or the more bonds we're making, the more energy gets released. So pretty straightforward there. So that's in Discord for us. So, but we can go ahead and take a look at this. So let's see, if we look at the Lewis structures here, what's actually happening. What are we making and breaking here? And I'm going to just go ahead and actually copy this down so we can see. Oh. So let's see what bonds we're breaking. These are going to be bonds in our reactants. So let's see, we have a bunch of CH bonds in our reactants. We have no CH bonds in the products. We always want to consider what bonds are being broken and what bonds are staying. In this case, we have CH bonds on the left, we have no CH bonds on the right, which means all CH bonds are broken. So we have 1, 2, 3, 4 CH bonds being broken. And let's see how many oxygen-oxygen bonds are being broken. We have the coefficient 2 to balance this out, which tells us we have 2 oxygen molecules. Let's look on the right and see how many O double bond O bonds we have. I do not see any O double bond O. I see O double bond C, but that's something different. O double bond O, we have to look if it's exactly the same bond on the other side. So we're breaking 2 O double bond O bonds here. We're breaking 2 of those. All right, so now let's look at the bonds formed, which is going to be our products. We see here we've made now 2 C double bond O bonds. Right, we have 1 here, 1 here. We have 2 C double bond O's that we're making. And we're making 1, 2. Remember, we have 2 of these, so each water molecule has 2 OH bonds. If we have 2 water molecules, then we have 4 OH bonds. So we're going to be breaking or forming 4 OH bonds. And so now we just have to look up these numbers. And that'll be our delta H. Equal this thing. So it'll be 4 times CH is 413. I'm going to ignore the units. This is all kilojoules per mole. O double bond O is 495. C double bond O, 799. And then OH is 463. And so, once again, I don't have my calculator here, shame on me, but we have cell phones, right? Let's go ahead and bust out our calculator. Okay, so 4 times 413 plus 2 times 495 minus 2 times 799 minus 4 times 463. Lo and behold, we get delta H equals negative 808 kilojoules per mole. Don't forget, now we can put the unit on, right? I just skipped it because of space concerns, but that's what we're expecting for this reaction based on the bond enthalpies. And let's see how right we are. Let's Google the answer and see what happens. What is the delta H for this reaction reported? Methane combustion. In reality, or experimentally, this depends on what we have. If we have liquid water or gaseous water, right? Um, gas water. Let's see if we can't get the one where it's. Aha. If we have gaseous water, it's negative 802 point, uh, um, say 6 kilojoules per mole. So this is if water is liquid. This is if water is gas. Remember that your state of matter does matter. Does matter. Um, it's important when you're doing delta HF, right? Because those have different values. And so experimentally, I mean, we calculated negative 808. So that's closer to this one. So probably we're looking at the gaseous water vapor for this reaction. And we're going to see that there's just a slight difference because of just some um, theoretical versus actual things happening here. So we see that in reality, we're looking at about 803. We calculated negative 808. So pretty close. Just by looking at what bonds are broken and formed using these numbers, we can figure this out. All right. All right, let's do another one. One that my organic students are doing. Just yesterday, I learned this reaction. We're going to chlorinate methane. We're going to make chloromethane and hydrochloric or hydrogen chloride. No water in this. So if we look at the Lewis structures, it's already balanced, by the way. I'm ignoring the lone pairs, but we don't need the lone pairs for this. But don't forget real Lewis structures. If I ask you for Lewis structures, make sure you include your lone pairs always. On your homeworks, do not forget your lone pairs. Okay, let's see what's being formed and what's being broken here. So broken goes first. It's positive values. These are things that will be in the reactants, but not in the products. So if we're looking at this, let's see what we have here. We have CH4, so CH 4 times, 4 CH bonds. In the products, though, we only have 3 CH bonds, which means we are breaking 1 CH bond. Right? Methane has 4 CH bonds, chloromethane has 3 CH bonds. So we've only broken one. We're also going to break, we have no Cl-Cl bonds in the products, so we're going to break that one. Minus, what are we making now? What's in the products that's not in the reactants? Well, we have one C-Cl bond, and we have one HCl bond. Those are the bonds that are being formed in this process. So, simply a matter of putting these together. So we have 413 plus Cl-Cl is, where are you? 242. CCl is 328. And then HCl, 31. Okay, and doing this, bust out your calculator again. 413 plus 242 minus 328 minus 431, and that equals negative 104 kilojoules per mole. And that's what we end up with as our delta H for this reaction. It is pretty amusing because I just did exactly the same thing yesterday. So I'll show you, we're not making this up. With some of the stuff we did, all sorts of fun stuff. Look what we did yesterday. Look what values we used. We used the same ideas that we're learning here, so don't forget them. So look what's happening here. We have some slightly different values here, and but notice what we have here. 104, negative 104 for our primary carbon hydrogen. So it is stuff that is useful. You will want to remember this for later. So it's good stuff. It's going to be used in OChem. So don't forget that. Okay, so these were the formed ones. Let's switch back here. So that's how we can calculate delta H from Lewis structures. We analyze what's being broken, what's being formed, and use the numbers that are provided for us. All right, so with this, I want to put kind of one more idea here. Which is that as bond order increases, that means we're going from a single bond to a double bond to a triple bond. That's a bond order. Single, double, triple, those are the bond orders, 1, 2, 3. We see that bond strength increases. And bond length decreases. So I ran out of space there, but let's look at some of these. So for these values, we have the I have the bond enthalpies here: 413, 614, and 839. These are the bond enthalpies. So we see here that it takes a lot more energy to break this, right? So it takes more energy to break this. And that means it's a stronger bond. Right? That kind of makes sense, right? The more energy it takes to break, the stronger it is. The more that you have to like smack it to get it to break open, the tougher it is. So stronger bond there. If we look at the actual bond length, the bond length for here is 1.54 angstroms, 1.34 angstroms, and then triple bond 1.2 angstroms. So as things are going to be bonding in higher bond orders, they get smaller and smaller, and it gets tougher and tougher to break those apart. So they're sharing more and more closely, and so it's tougher to break them apart. So this is just another trend, I suppose. So just keep that in mind as well. So you'll see things about like bond strength, bond length. All these things are related to each other. Alrighty. So the last question I'd like to go over is, are all these the same? Are all these bonds the same? And the answer is no, right? We've seen that these have different bond enthalpies, so not all bonds are the same. We're going to see that these three bonds are all pretty different from each other because we have different elements involved. And we're going to see we have another property of elements that we're going to relate to the periodic table, because you thought we were done relating trends and all that fun stuff. Nope. I'm going to talk about electronegativity. And it's similar to electron affinity, but we're going to see that it's actually better defined as the tendency of an atom to kind of, what's the best word to describe this? To kind of hoard electron density in a bond. So it's kind of like it's going to hog the electrons for itself. We have inequality here. We're going to see that if we look at something like this, the electronegativity values, I'll just tell you them, relatively speaking, are 4 and 2.1. I think I have a table of these in Discord, maybe I don't. I can put one. We're going to see that, here we go, this is electronegativity. We see these values will have a trend, just like before. And these are the tendencies of things to kind of hoard electrons. They withdraw them towards themselves, so they're not shared equally. So because nitrogen or fluorine has the higher electronegativity, it's more likely to kind of steal the electrons. So if we're looking at the actual bond, we kind of draw it like it's just this plain old equal thing. But in reality, it could be at any given time kind of closer to the H or closer to the F. And ideally, because this is a Lewis structure, we should have our other lone pairs on there. And this is the more reality one. So it's not quite in between them, as we might expect. Not in between them, it's not towards the H. The electrons are held more tightly towards fluorine. I mean, the electrons are kind of moving in between the two, right? But they just tend to spend more time hanging around fluorine because fluorine is more electronegative. It's got a more positive nucleus, right? That's one factor that relates with this. And so as a result, it tends to kind of keep the electrons towards itself more, which is going to create a partial charge on it. So full charges mean they have been given extra electrons. The fluoride ion has been given an electron from sodium or whatever, and it's actually moved from one atom to the other. However, in a covalent bond, we don't have full charges, but we can have partial ones. And we're going to see that in HF, the fluorine, because it's going to have electron density a little bit more, is going to be a little bit negative, which means the hydrogen is a little bit positive. And we call this a polar bond because it has a positive end and a negative end. It's polar. It's got poles. So it is a polar bond. We have something that's slightly negative, slightly positive. This is delta, by the way, the Greek letter delta. And it's a lowercase delta. So it's a delta plus, delta minus, partial charges. They're not full charges, as, say, something like sodium and fluorine would have. There's no sharing. There's no sharing, it's ionic, right? And we know that that's kind of metal, non-metal. These are our trends there. But really, it's all got to do with the electronegativity. If we hop over to Discord for a second, I keep pressing the wrong button. We pop over to Discord, we can take a look at these electronegativity values. If we look at sodium's, it's 0.9, fluorine's is 4.0. By the way, the trend is the same as effective nuclear charge. We see that top right is going to be the most electronegative. Let me just write that out as well. Or I'll write that out somewhere else, I guess, but right now we'll just take a look at these. We see the difference in electronegativity is much bigger than the difference was here. The difference in electronegativity is 1.9 for HF. For NAF, it's 3.1. That's the difference in their electronegativity values. And so that's why this is an ionic compound. We see that as we get to a bigger and bigger difference in electronegativity, the more likely it is we're just going to steal it. And in reality, this is a spectrum. Covalent and ionic are really a spectrum. It's kind of hard to say, well, is the electron still being shared or is it fully taken away? We don't really have an exact line, but we have some guidelines. Generally speaking, we're going to see that if you have a, uh, a difference in electronegativity that is bigger than 1.9, you're ionic. Not including 1.9, but bigger than. That is a fully ionic bond, we'll say. We say if you're between 0.4 and 1.9, including 1.9, that is a polar covalent bond. That is a polar covalent bond. And if you're 0.4 or less, I'm sorry, I said it the other way. If you are less than 0.4, then you are just a non-polar. There's really no, if it's not a significant difference in electronegativity, electrons are effectively equally shared. These are kind of guidelines. So they're helpful in kind of us helping to make these decisions, but we generally consider things that fall in these categories to be ionic, polar covalent, and non-polar covalent, even though it's a spectrum. So at 0.4 exactly, is it kind of, it's I don't know, it's both. Polar, it's non-polar, it's kind of just its own little shade of polar. It's slightly polar, we'll say. So we're looking at the difference of electronegativity between things. That's something that's going to help us determine this. Of course, if you have two of the same thing, fluorine molecule F2, delta En 0, right? So it's completely nonpolar, absolutely nonpolar. And the reason it's nonpolar, of course, is because there's no reason that the electrons are more likely to be with one fluorine than the other, right? It makes no sense. Why would they choose the fluorine on the right versus the fluorine on the left? They're equally attracted to both, so they're more likely to just hang out in the middle, no polarity. Polarity arises when there's an unequal sharing, when the electrons are more attracted to one than the other one. And so the fluorine, being the most electronegative, typically will gather things towards itself. And so we see these things happen. And let's see. Let's take a look at this molecule. If we do its Lewis structure, we're going to see that The electronegativity of oxygen is 3.5. For fluorine, it's 4.0. Again, I've given these values to you on Discord. They're also very easily looked up. Wikipedia, an electronegativity table, and you'll be able to find them. The book has one as well. The difference here is 0.5, which means we're going to put this as a polar bond. And if it's a polar bond, we have to indicate that by putting delta charges. So you want to put the negative with the more electronegative atom and the positive with the less electronegative atom. So the fluorines here are slightly positive. I don't want to say 8 plus. Let's try that again. There we go. I'm sorry, those are negative. Oh my gosh, I even said that. These are delta negatives. Fluorine will always be delta negative, by the way, unless it's with itself. But the oxygen will be the slightly positive one. And there's no need to put two delta positives because it's just, these are partial charges. We don't really worry about the magnitude too much. You can calculate it if you really want to. There is a formula for it. Q times D will give you the dipole, but we'll talk about that next week. So we'll worry about that later. So with this, the idea here is that we have an uneven sharing of electrons. And we're going to see next week how having polar bonds in a molecule will affect the entire molecule overall. And then the week after that, we'll explore what happens as a result. So this will be an ongoing discussion of polarity that we have. So for right now, when you're looking at Lewis structures, you want to be looking at, where did I put that? Oh, here it is. Ionic ones are 2 and above, polar covalent ones in between, and then the nonpolar are less than 0.4. So these will be important considerations to do. It'd be a good idea to go back through all the problems we've done and try and figure out if they're polar or not, if the bonds are polar. Be a good practice to do that. I just want to put the trend out here as well. Typically, we see that electronegativity increases as we go up and to the right. So fluorine is our most electronegative, and francium would be our least. The noble gases, by the way, we don't keep electronegativity values for noble gases because they don't typically make bonds. There are some estimated ones for xenon and krypton because they will react with fluorine under the right conditions, but the rest of the noble gases just do not have electronegativity values because they don't make bonds, so there's no need to have an uneven sharing idea. So we have that. For the record, let's see what xenon's is. Xenon's electronegativity is 2.6. So if we were to look at xenon that we did earlier, we would see, where is it? There it is. We would see that all these guys then would be, all the fluorines would be partially negative, the xenon would be partially positive. The difference of electronegativity here is 1.4, which puts them as polar covalent bonds. All right, so metals, as you would imagine, need to have particularly low electronegativities in order to actually make ionic bonds, and typically those are done with halogens or oxygen, not really so much sulfur, but that's the idea. All right, so that's the idea here. So that's all we needed to do today. So a couple new topics. You are fully capable of doing the homework here. So get started. Even though, yes, I know you have an exam. Your exam's only on 2 chapters. They're not that difficult, I would say, compared to our second exam, but be a good idea to not let this pile up on you. Again, that's another reminder, so keep that in mind. All right, so we're good. That's it for today. Study well. Have a nice weekend. I did send out an email yesterday, so check on that if you want, and let me know your thoughts on it. And I'll try and have your stuff graded today or tomorrow, so you have as much information as necessary to make a decision. Okay? Alrighty then. Take care, everybody. See you on Tuesday. Good luck on your exam.